Before we can understand the largest stars, we need to establish a baseline. And that baseline is the sun, the star, the one that lights your days and makes life on Earth possible. The sun is enormous by human standards. Its diameter is 1.4 million kilometers, 109 times wider than Earth. You could line up 109 Earths across the sun's diameter. In terms of volume, you could fit 1.3 million Earths inside the sun. If Earth were a peppercorn, the sun would be a sphere 8 inches across, about the size of a grapefruit. The sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust, is a rounding error. Jupiter, the largest planet, is only 0.1% the sun's mass. Earth is 0.003%. Standing on Earth, the sun looks small, a bright disk you can block with your thumb. But that's only because it's 150 million kilometers away. If you could somehow stand on the sun's surface, you can't, you'd be vaporized instantly. The horizon would curve away in every direction, impossibly distant. Walking at a steady pace, it would take you 10 years to walk around the sun's circumference. The sun's core, where nuclear fusion occurs, reaches 15 million degrees Celsius. The pressure is 250 billion times Earth's atmospheric pressure. Every second, the sun converts 600 million tons of hydrogen into helium, releasing energy equivalent to exploding 100 billion megatons of TNT. That energy radiates outward, taking hundreds of thousands of years to work its way from the core to the surface, where it finally escapes as light. This is our reference point. This incomprehensibly large, powerful object is small by stellar standards. It's a yellow dwarf, an average medium-sized star, unremarkable in almost every way. And there are stars that make the sun look like a grain of sand on a beach. Before we can understand the largest stars, we need to establish a baseline. And that baseline is the sun, the star, the one that lights your days and makes life on Earth possible. The sun is enormous by human standards. Its diameter is 1.4 million kilometers, 109 times wider than Earth. You could line up 109 Earths across the sun's diameter. In terms of volume, you could fit 1.3 million Earths inside the sun. If Earth were a peppercorn, the sun would be a sphere 8 inches across, about the size of a grapefruit. The sun contains 99.86% of all the mass in our solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust, is a rounding error. Jupiter, the largest planet, is only 0.1% the sun's mass. Earth is 0.003%. Standing on Earth, the sun looks small, a bright disk you can block with your thumb. But that's only because it's 150 million kilometers away. If you could somehow stand on the sun's surface, you can't, you'd be vaporized instantly. The horizon would curve away in every direction, impossibly distant. Walking at a steady pace, it would take you 10 years to walk around the sun's circumference. The sun's core, where nuclear fusion occurs, reaches 15 million degrees Celsius. The pressure is 250 billion times Earth's atmospheric pressure. Every second, the sun converts 600 million tons of hydrogen into helium, releasing energy equivalent to exploding 100 billion megatons of TNT. That energy radiates outward, taking hundreds of thousands of years to work its way from the core to the surface, where it finally escapes as light. This is our reference point. This incomprehensibly large, powerful object is small by stellar standards. It's a yellow dwarf, an average medium-sized star, unremarkable in almost every way. And there are stars that make the sun look like a grain of sand on a beach. The first step up from the sun brings us to giant stars that have exhausted the hydrogen in their cores and begun to evolve. When a star like the sun runs out of hydrogen fuel in its core, the core contracts and heats up. Hydrogen fusion moves to a shell around the core. The outer layers expand and cool. The star becomes a red giant. Our sun will do this in about 5 billion years. When it does, it will swell to roughly 100 times its current diameter. Its surface will extend past Mercury's orbit, possibly past Venus's, maybe even reaching Earth. If you're standing on Earth billions of years from now, you won't be life will have already been sterilized by the increasing heat. You'll watch the sun grow larger and larger in the sky until it fills the entire horizon, a wall of red fire consuming the world. But the sun's red giant phase is modest compared to other stars. Consider Arcturus, a red giant about 25 times larger than the sun. If you replaced the sun with Arcturus, Earth would orbit inside its outer atmosphere. Or Aldebaran, the orange eye of Taurus the Bull, about 44 times the sun's radius. This star has swollen so much that its density is incredibly low. The outer layers are thinner than the air you're breathing, despite temperatures of 3,000 degrees. These are giant stars. They're the beginning of stellar obesity, stars that have inflated beyond their main sequence sizes, trading density for volume. But they're still small compared to what comes next. Supergiants are where scale truly begins to break down. These are stars that started with far more mass than the sun, 10, 20, 50 times as much. They burn through their fuel at incredible rates, shining with the luminosity of hundreds of thousands of suns, and they swell to sizes that make red giants look tiny. Consider Betelgeuse, the red supergiant marking Orion's shoulder. Betelgeuse is about 700 to 900 times the radius of the sun. Its size varies as it pulsates. If you placed Betelgeuse where the sun is, its surface would extend past Mars's orbit, possibly reaching Jupiter. Imagine that, a star so large that Mars would be inside it. Jupiter, a gas giant 11 times wider than Earth, a planet so massive it could fit 1,300 Earths inside, would be near or inside the star's outer atmosphere. Betelgeuse is massive enough that its volume could contain approximately 1.6 billion suns, not Earths, suns, and Betelgeuse isn't even the largest supergiant. Antares, another red supergiant, is roughly 700 to 900 times the sun's radius, comparable to Betelgeuse. VY Canis Majoris, once thought to be the largest star, is about 1,420 times the sun's radius. Its volume could fit roughly 3 billion suns. These stars are so diffuse, so inflated, that their outer atmospheres have densities lower than laboratory vacuums on Earth. If you could somehow enter one, you'd pass through what technically counts as the surface without immediately noticing. The gas would gradually thicken as you descended, the temperature rising, until deep in the interior, the pressure and heat would obliterate anything made of matter. Supergiants don't last long. A star like Betelgeuse has only existed for about 10 million years, nothing in cosmic time. It will explode as a supernova soon, possibly within the next 100,000 years, possibly tomorrow. When it does, it will briefly shine as bright as the full moon, despite being 650 light years away. The explosion will be visible during the day, but even supergiants aren't the largest stars we've found. We've reached the absolute limit, the largest stars known to exist. Stars so massive, so inflated, that they shouldn't be stable. Stars at the edge of what physics allows. These are the hypergiants. Stephenson 2 to 18 holds the current record. Located about 19,000 light-years away in the constellation Scutum, buried deep in a massive star cluster, Stephenson 2 to 18 is a red hypergent with a radius approximately 2,150 times larger than the Sun. Let that sink in. If you placed this star where our Sun is, its surface would extend beyond the orbit of Saturn. Mercury, Venus, Earth, Mars, Jupiter, and Saturn would all be inside the star. Only Uranus and Neptune would orbit outside it. The volume is almost impossible to comprehend. Stephenson 2 to 18 could contain approximately 10 billion suns. Not 10 billion Earths, 10 billion suns. Each one of those suns could itself contain 1.3 million Earths. If you do the math, Stephenson 2 to 18 could fit roughly 13 quadrillion Earths inside its volume. That's 13 quadrillion Earths. The number is so large it stops meaning anything. Light takes 8.7 hours to cross from one side of Stephenson 2 to 18 to the other. If you somehow traveled at the speed of a commercial jet 900 kilometers per hour, it would take you 1,100 years to fly from one side to the other. But Stephenson 2 to 18 isn't alone. OG-64 is another extreme hypergent, possibly even larger, though measurements are uncertain. Located in the Large Magellanic Cloud, it's surrounded by a torus of dust and gas ejected from its outer layers, evidence that the star is tearing itself apart. UY Scuti was once thought to be the largest, with radius estimates around 1,700 times the Sun. More recent measurements have revised this downward, but it's still one of the most massive objects ever found. RW Cephei, Westerlund 1 to 26. VV Cephei A, the list of hypergents goes on. Each one a monster, each pushing the boundaries of stellar physics. These stars share common traits. They're incredibly luminous, shining with the power of hundreds of thousands or millions of suns. They're unstable, pulsating, shedding mass in powerful stellar winds. They're dying, having burned through their hydrogen and moved on to fusing helium, carbon, oxygen, and heavier elements in their cores. And they're short-lived. A hypergent like Stephenson 2 to 18 might exist for only 3 to 5 million years. For comparison, the Sun will live for about 10 billion years. Hypergents burn bright and die young. They're also incredibly rare. In our entire galaxy of 200 to 400 billion stars, there are perhaps only a few dozen hypergents. They represent a brief, extreme phase of stellar evolution, the final act before a catastrophic supernova. You're witnessing the largest objects capable of existing as stars. Anything larger would be gravitationally unstable, unable to maintain spherical form. Anything more massive would rip itself apart with radiation pressure. Stephenson 2 to 18 is at the limit, the edge of what's possible, and standing before it, even hypothetically from a safe distance, would be like standing before infinity. What would it actually be like inside one of these hypergent stars? Imagine you could somehow survive the journey. You can't. But imagine and descend from space toward Stephenson 2 to 18. From a distance, it dominates everything. A massive sphere of dull red light, so large it fills your entire field of vision long before you reach it. It doesn't look like the sun-bright, sharp-edged, painful to look at. It looks like a vast, diffuse fog of glowing gas. As you approach what you'd call the surface, you pass through the stellar, winged streams of gas being blown off the star by radiation pressure. The wind carries away mass equivalent to several Earths per year. The star is literally evaporating, losing itself to space. You reach the photosphere, the visible surface, but there's no sharp boundary. The density gradually increases. The temperature rises. What counts as surface is arbitrary, just the depth where the gas becomes opaque enough that you can't see through it anymore. The temperature here is relatively cool for a star, maybe 3,500 Kelvin, 3,200 degrees Celsius. Hot enough to vaporize any known material, but cool compared to the sun's 5,800 Kelvin surface. The density is astonishingly low. The outer atmosphere of Stephenson 2 to 18 is less dense than Earth's atmosphere at sea level, less dense than the air you're breathing. In some regions, it's closer to a laboratory vacuum. You could pass through what technically counts as the star's interior without immediately being crushed or incinerated, though you'd eventually die from heat and radiation. As you descend deeper, things change. The gas thickens. The temperature climbs. The pressure increases. Convection currents larger than planets churn the gas, carrying heat from the interior toward the surface. Deeper still, hundreds of thousands of kilometers down, you reach regions where the gas becomes plasma, electrons stripped from atoms by heat and pressure. The temperature is tens of thousands of degrees. The density approaches water, then exceeds it. At the core, conditions become extreme. The temperature reaches 100 million degrees or more. The pressure is billions of times Earth's atmospheric pressure. Here, nuclear fusion occurs, not just hydrogen fusing into helium like the sun, but heavier elements. Helium fusing into carbon and oxygen. Carbon fusing into neon and magnesium. Oxygen fusing into silicon and sulfur. The core of a hypergent is an onion of shells, each fusing different elements, each layer releasing energy that supports the star against gravitational collapse. It's a delicate balance, and it won't last. The core is creating iron, and iron is the end. Fusing iron doesn't release energy, it consumes energy. Once the core is full of iron, fusion stops. The energy supporting the star shuts off, and gravity wins. What happens next is one of the most violent events in the universe. Hypergents exist because they started with enormous mass 50, 100, perhaps 150 times the sun's mass, and evolved rapidly. Massive stars burn hot and fast. The more massive a star, the higher the core temperature needed to support itself against gravity. Higher temperatures mean faster fusion rates. Faster fusion means shorter lifetimes. The sun will live for about 10 billion years, slowly fusing hydrogen into helium in a stable main sequence phase. A star with 50 times the sun's mass might live only 5 million years. A star with 100 solar masses might last only 2 to 3 million years. These massive stars race through their fuel. Hydrogen burns away in 1 million years. They move on to helium fusion, swelling into supergiants. Then carbon, oxygen, neon, magnesium, silicon, each stage shorter than the last. Silicon fusion, the final stage before iron, lasts about 1 day. As they evolve, they inflate. The outer layers expand, cool, and become red. The star becomes a hypergent massive in volume, but relatively cool on the surface. But this can't last. The core is building up iron, and when the core becomes iron, the end is seconds away. The core collapses. In less than a second, a region the size of Earth containing more mass than the sun collapses to a point 20 kilometers across. The implosion is so violent it rebounds, sending a shock wave outward through the star. The shock wave tears the star apart. The outer layers, most of the star's mass, explode into space at 10% the speed of light. The explosion releases more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. This is a supernova, specifically a Type II supernova, the death of a massive star. For a few weeks, the supernova shines as bright as an entire galaxy, billions of stars. Then it fades. What's left behind is either a neutron star, a 20-kilometer sphere so dense that a teaspoon of its material weighs as much as a mountain, or a black hole. If the core was massive enough, the explosion scatters heavy elements into space: carbon, oxygen, iron, gold, uranium. These elements, forged in the star's core and in the explosion itself, mix with interstellar gas. New stars form from this enriched material. Planets condense. Life eventually arises. You are made of material forged in dying stars. The iron in your blood, the calcium in your bones, the oxygen you breathe, all created in stellar furnaces and scattered by supernova. Hypergents are rare because they exist for such a brief time. At any given moment, there are only a handful in the galaxy, but over cosmic time, there have been millions, and their deaths seed the universe with the elements necessary for planets and life. Stephenson 2 to 18 will explode. Maybe in 1,000 years, maybe in 1,000,000, but soon on cosmic timescales. When it does, it will briefly be one of the brightest objects in the sky, visible during the day despite being 19,000 light years away. And then it will be gone. The largest star we've ever found, reduced to a neutron star or black hole, its mass scattered across light years of space. Try to imagine it. Really try. You're in a spacecraft approaching Stephenson 2 to 18 from a safe distance, say 20 astronomical units away, about the distance from the Sun to Uranus. The star fills your view, not partially, not mostly, completely. It's a wall of dull red light stretching in every direction. You can't see its edges. They're beyond the limits of your peripheral vision. It's like standing on Earth and trying to see the entire sky at once. The star is the sky. You're looking at an object 2,150 times wider than the sun, and object that could contain 10 billion suns, an object so large that light takes nearly 9 hours to cross it, and you can't grasp it. Your brain evolved to understand sizes from centimeters to kilometers, mountains, oceans, continents. Even Earth as a whole is comprehensible. You can see pictures of it from space. You can conceptualize its surface. But this? A star whose volume could fit 13 quadrillion Earths? You can say the number. You can write it down. You can calculate it. But you can't understand it. Not really. The scale is too large. It breaks human intuition. And here's the profound part. Stephenson 2-18 is at the absolute limit of what's possible. It's the largest type of object that can exist as a star. Go any bigger, and physics says no. Radiation pressure would tear it apart. Gravity couldn't hold it together as a sphere. This is the edge, the maximum, the final boss of stellar scale. And yet, in cosmic terms, it's temporary, fragile, dying. Stephenson 2-18 has existed for maybe 4 million years. It will explode in a supernova soon, perhaps in the next 100,000 years, perhaps tomorrow. Its life is a brief flash. Compared to stable stars like the Sun, these hypergents, the largest objects in the universe, are also among the most fleeting. They burn bright and die young. They exist at the extremes of physics, where the rules barely hold, where stars become so bloated they're almost not stars anymore, but spheres of glowing gas held together by the thinnest margin. And when they die spectacularly. Supernova that briefly outshine entire galaxies. Explosions that seed the cosmos with heavy elements. Deaths that make life possible. You are here because stars like this existed, lived briefly, and exploded. The elements in your body were forged in stellar furnaces like Stephenson 2-18's core. Your existence is a consequence of their deaths. So when you look at the largest star in the universe, you're not just seeing an object of incomprehensible scale. You're seeing your ancestor, the crucible that created the raw materials for planets, for oceans, for life, for you. Stephenson 2-18 is vast beyond comprehension. But it's also connected to you in the most fundamental way. You're made of stars, and the largest stars made the heaviest elements, which means you carry within you the legacy of the biggest, brightest, most extreme objects in the cosmos. That's not just scale, that's poetry written in physics. That's the universe contemplating itself through you. The largest star in the universe is so big that 10 billion suns could fit inside it. That sentence is factually accurate and completely meaningless to human experience. You've never seen 10 billion of anything. You probably haven't seen 1 million of anything all at once. And these aren't small objects, these are suns. Each one massive enough to dominate a solar system. Each one capable of fitting 1.3 million Earths. And 10 billion of them fit inside Stephenson 2-18. The numbers work. The physics is sound. But comprehension fails. And maybe that's the point. Maybe the universe isn't meant to be fully comprehended. Maybe these hypergent stars exist to remind us that reality is larger, stranger, and more extreme than our everyday experience suggests. Stephenson 2-18 is a monument to the limits of physics. It's as large as a star can be and still be a star. It exists at the boundary between possible and impossible, held together by the thinnest margin, destined to explode in one of the most violent events the universe can produce. And yet, despite its size, despite its power, despite the fact that it will explode with the force of 100 billion megatons, temporary, ephemeral, a brief flash in cosmic time, the sun is unremarkable, average, boring by stellar standards. But it will outlive Stephenson 2 to 18 by a factor of 3,000. Slow and steady wins the race. The largest is not the longest lived. What does this tell us? Maybe that bigger isn't always better. Maybe that extremes are unstable. Maybe that the universe favors balance over excess. Or maybe it tells us that the universe explores every possibility. Small stars, large stars, everything in between. Stable stars that burn for trillions of years. Hypergents that blaze for millions and die in glory. The cosmos tries everything. And you standing on a planet orbiting a medium-sized yellow star, you're here because some of those hypergents lived and died. They fused elements. They exploded. They scattered their material into space. That material formed new stars, new planets. And on at least one of those planets, that stardust became you. Stephenson 2 to 18 is vast, incomprehensibly vast. But you're the part of the universe that can comprehend or try to comprehend its vastness. You're the stardust that learned to wonder about stars. And that might be just as remarkable as the star itself.